Hello and welcome to this lesson on DevOps Overview. I am Mahendra Mehra and I am a Senior Training Lead and Evangelist with Oracle University. So let's get started. Let's try to understand DevOps through a story. Head and Heart Holistic Healthcare is a mid-sized business that develops healthcare and wellness software applications. During the COVID pandemic, their business skyrocketed and they are being challenged to scale their development and operations very rapidly. The company started with the waterfall model of development 10 years ago, and since last 5 years they've been using the agile model. However, they are struggling to keep up with the customer demand and the competitive marketplace. Let's meet our key players and listen to some of the specific challenges that everyone is facing. Meet Jamal from the development team and Trisha from the operations team. The relationship between developers and IT operations is often adversarial. Typical challenges for developers such as Jamal include being pressured for on-time delivery, grappling with issue resolution, implementing new application capabilities, ongoing need for code management, and long and slow software release cycles. Typical challenges for operational leads such as Trisha include resource contention, analysis and diagnostic checks, fast issue resolution, constant demand for redesign, and keeping up with the customer request to edit or tweak. When a client has complaints about a software, the blame is internally thrown at each other. The developer team would point fingers at the IT ops team and then who would redirect the same blame to the dev team. For example, Jamal would say the code worked perfectly on his machine, where Tisha can argue that the code submitted by Jamal wasn't proper and it broke in the production environment. So overall, what developer wants is frequent changes to be pushed to production environment, whereas the operations want prod environment to be stable. But what business needs is both, that is quick changes and stability at the same time. Meet Ramona, the CEO of Head and Heart Holistic Healthcare. She has heard from both her development and operational leads, and she knows they are struggling and working in their own silos, which is negatively impacting the company. She then makes a call to an Oracle architect, Mo, and shares some of her specific concerns. She tells Mo about how her team can't seem to coordinate their production activities and tasks. She then goes on to explain about the customer losses and complaints, as well as the mounting opportunity cost and the strategic impacts on the business and the financial plans. She asks for help. Mo, the Oracle architect, listens patiently and then offers a resounding yes in order to help her overcome these challenges. Ramona and Mo spend an hour on the phone and Ramona outlines her issues like deployment delays, high operational cost, communication issues, problems with security, high failure rate, erratic code execution, and no plan to implement continuous integration. Mo takes notes but knows all along that he has a perfect solution and asks Ramona if she has heard about DevOps service, and then goes on to explain her regarding the OCI DevOps services. Now that we know the challenges a software development team faces who uses a traditional software development approach, let's try to understand what DevOps is and how it helps overcome these challenges. Let's begin with DevOps definition. DevOps is a way of working that allows for continuous delivery. DevOps encourages collaboration between teams such as development and operations who are working in silos. DevOps enables automation, basically using automation tools that can leverage an increasingly programmable and dynamic infrastructure, which helps in increasing the pace of releases, improve your product faster, and build competitive advantage. DevOps instills a continuous culture where it represents a change in IT culture focusing on rapid IT service delivery through the adoption of agile, lean practices in the context of system-oriented approach. For DevOps to be effective, all what is required is a paradigm shift. Enterprises must make this paradigm shift to digital transformation. So we have defined what DevOps is. Now let's discuss why it matters. DevOps brings development and operations team together to create a unified infrastructure. And this team collaboration maximizes productivity, simplifies the software production lifecycle, makes each phase programmable and dynamic, helps you improve release and deployment frequency, along with maximizing predictability, efficiency, and security. It aids in release management and helps you find bugs early in the software development lifecycle. Let's look at the DevOps lifecycle. It is defined as a rapid release, multi-phased software development lifecycle, and in addition to having a built-in strong feedback loop, this lifecycle is stress-driven to ensure robust software and uses code that is continuously built, tested, released, and monitored. Now let's have a look at the lifecycle phases. On the dev side, you have plan, code, build, test, and on the operation side, you have release, deploy, operate, and monitor. So we have defined the DevOps software development lifecycle and its 8 phases. Let's take another view and look at these phases laterally. So the phases are plan, code, build, test, release, deploy, operate, and monitor. The agile development covers phases like plan, code, and build, where it organizes work in short iteration called sprints to increase the number of releases. Agile emphasizes on software development methodology for developing the software. When the software is developed and released, the agile team will not care what happens to it. Continuous integration, on the other hand, requires developers to integrate their work with one another as early as possible in the life cycle. This helps exposing bugs and issues on a regular basis. Continuous delivery provides tools and best practices to deliver quickly. At the end of each CI build, software is delivered for QA testing and then for delivery to the production environment. And as you can see, continuous delivery stretches out up till the deploy phase. But what about continuous operation and monitoring? This is where DevOps comes into picture. DevOps is to give end-to-end business solution for faster delivery of products to the market. DevOps is all about taking software which is ready for release and deploying it in a reliable and secure manner. So now you know what CI and CD are, but as we said earlier, DevOps is an entire paradigm shift and it instills a continuous culture. That means that DevOps is all about continuity at every stage of the life cycle. It's a process for iterative software development and is an umbrella over several other continuous processes, including continuous development, continuous testing, continuous release and deployment, continuous monitoring, and continuous feedback and optimization. Adapting DevOps to support the entire software development lifecycle with an emphasis on agility and efficiency regardless of function provides several benefits. Some of these benefits include a curated culture, where your teams are more connected and the workers are more efficient, where you have greater employee engagement and collaboration with increased personal and professional growth opportunities. The other benefit includes tighter technicality, which provides improved overall software quality with more simplicity and less complexity. It provides quick problem resolution and greater stability and reliability with continuous delivery. The DevOps benefit also leads to better business yields with lower IT cost, quick delivery times, more predictability, increased flexibility, and heightened innovation. To wrap up, in this lesson we understood the drawbacks of traditional approach in software development and realized how DevOps effectively serves the purpose of reducing the time involved in software development lifecycle for prompt deliveries and securing continuous production of high-quality, foolproof software applications. I hope you found this lesson useful. Thanks for watching. Hello and welcome to this lesson on OCI DevOps Service. Before we define the specifics of OCI DevOps as a service, let's generally define the DevOps in the cloud. DevOps automation is becoming cloud-centric. Most public and private cloud computing providers support DevOps systematically on their platform, including continuous integration and continuous development tools. This tight integration lowers the cost associated with on-premises DevOps automation technology and provides centralized governance and control for a sound DevOps process. DevOps in cloud is a suite of managed cloud-based tools that forms a pipeline for code and bug tracking, automated unit testing and deployment, and reviewing and monitoring. Now, the question is, why use DevOps in cloud? There are several reasons why customers would want to use DevOps in the cloud. Some of those reasons include it saves time and energy. Building DevOps infrastructure requires a lot of work. A pre-built solution will save time and energy. Next is it collapses into single silo for collaboration. DevOps minimizes the silos and gaps by eliminating the boundaries between the conventional developer and the operation rules. This ensures business continuity, accountability, and desired results across groups. DevOps also helps you automate the entire deployment process. It helps you lower cost for development, testing, deployment, and operations. It's much easier to track cost of development resources and make adjustments as needed. Let's understand OCI DevOps as a service in more detail. The Oracle Cloud Infrastructure DevOps service is an end-to-end continuous integration and continuous delivery platform for developers. This service makes it easy to build, test, and deploy software and applications on the Oracle Cloud. With the help of OCI DevOps service, you can create private code repositories to store and manage source codes. You can also mirror external repositories from GitHub, GitLab, and Bitbucket Cloud to OCI code repositories. It helps you build and test your latest changes in a build pipeline with a service-managed build runner. You can set up a trigger to automatically run your build pipeline from a source code commit or pull request. Optionally, you can run a deployment pipeline on the successful build run for a complete CI/CD automation. It lets you orchestrate your software deployment across regions to OCI platforms such as Container Engine for Kubernetes, also known as OKE, and compute instances and functions. It helps you avoid downtime during deployments through the blue-green and canary deployment strategies. It helps you automate the complexity of updating applications. Automation reduces the chance of human error that might introduce a security vulnerability. It enhances the security and reduces risk in delivery. As DevOps enables faster software delivery, security bugs can be resolved quickly by rolling out a fix. Let's take a look at some of the DevOps as a service benefits. The first benefit is automation. The OCI DevOps service fully automates the software delivery lifecycle and thereby increases the speed of development and reliability of application delivery. It eliminates manual error-prone methods of application integration and deployment and increases the reliability of operations. Next is scalability. OCI DevOps service scales your builds with service-managed build runners. You can run concurrent builds and don't need to manage or operate the underlying build runner host. Integration and interoperability. DevOps service works with your existing Git repositories and continuous integration systems for customers building new cloud-native applications or migrating existing applications to OCI. The DevOps service is integrated with OCI services such as virtual machines, Oracle Container Engine for Kubernetes, Oracle Functions, artifact repositories, vault secrets, policies, and much more. Low risk of deployments and faster time to market. With OCI DevOps deployment pipelines, you can reduce change-driven errors introduced by manual deployments. Instead, perform rolling, canary, or blue-green deployments and optional automated rollbacks. All these capabilities lead to reduced risk, complexity, and eliminate downtime of your production applications. Last but not the least is the low cost. For deployments, customers pay only for the resources used by the targets of their software deployments. To wrap up, in this lesson we introduced you to OCI DevOps service and discussed the benefits it offers to developers to simplify the software delivery lifecycle. To all the DevOps enthusiasts who wish to get started with the DevOps service, I would recommend that they go through the OCI DevOps Professional Learning Path. I hope you enjoyed this lesson. See you in the next one. Thanks for watching. Hello and welcome to this lesson centered around developing cloud-native solutions on OCI. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Throughout this lesson, we'll embark on a comprehensive exploration of OCI's cloud-native services, all within the context of an engaging and enlightening case study. Let's get started. Trisha, an Oracle client, engages with Steve, who's an Oracle consultant. Trisha initiates the conversation by expressing her concerns about migrating her static website to the cloud with new feature enhancements, specifically on Oracle Cloud Infrastructure. Steve reassures her, emphasizing the benefits of moving to Oracle Cloud Infrastructure and highlighting the potential to enhance the website's capabilities. Steve then asks Trisha about cloud-native approach, to which Trisha expresses familiarity but admits she is unsure of its specifics. Steve offers to explain further, indicating his readiness to clarify any uncertainties Trisha may have. Steve proceeds to explain the concept of cloud native. He describes it as the approach to building and running applications that leverage the distributed computing capabilities of the cloud. Cloud-native apps are designed to capitalize on the scale, elasticity, resiliency, and flexibility offered by the cloud. Steve highlights various technologies that enable cloud-native development, including microservices and containers, Kubernetes and service mesh, serverless functions and APIs, Kafka, and DevOps practices, as well as CI/CD pipelines. He emphasizes that OCI provides tools and services to streamline development, reducing operational tasks, and enabling faster applications deployment. Ultimately, cloud-native architectures facilitate loosely coupled systems that are resilient, manageable, and observable, empowering engineers to make impactful changes with ease. Trisha expresses her desire for a comprehensive overview of cloud-native services offered by Oracle Cloud Infrastructure. Steve agrees, acknowledging the importance of understanding Trisha's requirements before delving into the details of OCI's cloud-native service offerings. Let's use Trisha's website enhancement project as a case study to illustrate how various OCI service offerings can enhance the Vision Stays website and streamline future development and operations for Trisha's team. Let's understand Trisha's requirement in more detail. A hotel chain, Vision Stays, has a static website, that is its current form, and now they are interested in building a hotel booking facility to expand and enhance the website for their customers. They want to add a booking functionality, also some integration capabilities which will allow for third-party hotel aggregators to inquire about their hotel room availability and to book Vision Stays hotel rooms. They are looking at utilizing OCI cloud-native solutions to host and enhance features of their website. This is what is the current state of the Vision Stays static website, and this is how it would appear with the new enhancements. Let's understand this entire case study in different steps. The first step focuses on migrating the static website to an OCI compute instance. This involves transitioning the website's files, including HTML, CSS, JavaScript, and media assets to a virtual machine provisioned within the Oracle Cloud Infrastructure environment. By utilizing a VM for hosting the static website, we leverage OCI's robust compute capabilities to ensure reliable performance and scalability. Subsequently, we'll incorporate an OCI load balancer to function as the front end of the website. The OCI load balancer acts as a traffic distributor, intelligently distributing incoming requests across multiple backend VM instances hosting the static website. This ensures optimal resource utilization and enhances website's availability and responsiveness. Additionally, the load balancer provides advanced traffic management features such as SSL termination, session persistence, and content-based routing, further enhancing the website's security and performance. It's crucial to establish IAM policies to govern the teams involved in deploying the website on OCI. IAM policies play a critical role in ensuring secure access and management of resources within OCI. By setting up IAM policies, we can control and restrict access to specific resources, ensuring that only authorized individuals or teams can perform certain actions. This helps maintain data confidentiality, integrity, and availability, ultimately enhancing the security posture of the environment. Now, once the static website is deployed on the Oracle Cloud Infrastructure platform, we can focus on implementing a microservices architecture to introduce new functionalities to the Vision Stays website. This approach involves breaking down the monolithic architecture into smaller, independent services known as microservices to enhance the scalability, agility, and maintainability. To achieve this, we'll employ various OCI services to facilitate different aspects of the microservices architecture. We can deploy certain microservices as containers within OKE, which is Container Engine for Kubernetes Service. OKE provides a scalable and flexible platform for managing containerized applications, offering features such as automated provisioning, scaling, and orchestration. Some microservices will be implemented using OCI functions. These functions execute code in response to events, providing a lightweight and scalable solution for handling specific tasks within the application. Container images and other artifacts required for the microservices will be stored in the OCI Container Registry and Artifact Registry. These services offer secure and scalable storage for container images and artifacts, ensuring efficient management and distribution across development and deployment environments. We can utilize Oracle API Gateway service to enable communication between the deployed microservices and external clients. API Gateway acts as a centralized entry point for accessing and managing APIs, providing features such as authentication, authorization, rate limiting, and traffic routing. By leveraging API Gateway, we ensure secure and efficient communication between microservices and external systems, enabling seamless integration and interoperability. We will leverage new serverless autonomous database for storing persistent data required by the microservices. Oracle's autonomous database offers a fully managed, self-driving database solution that automatically handles database provisioning, scaling, and patching, reducing operational overhead and ensuring high availability and performance. A web application firewall policy can be implemented to enhance the security of the Vision Stays website. Web Application Firewall provides protection against common web application threats and attacks, safeguarding the website from potential security vulnerabilities and breaches. The development to deployment process will be automated using DevOps Project and Resource Manager. DevOps Project enables streamlined collaboration and automation across the software development lifecycle, while Resource Manager facilitates infrastructure creation and management through code and templates, ensuring consistency and repeatability in infrastructure deployments. Service Mesh within OCI can be used to facilitate communication between microservices, which improves reliability and enhances observability within the distributed architecture. Lastly, we'll utilize core OCI services such as logging, notifications, and secrets encryption with OCI Vault to enhance operational visibility, monitor applications' performance, and ensure secure management of sensitive data and credentials. I hope you're liking this video so far. See you in the next one. Thank you for watching. Welcome back. Let's continue from where we left off in the previous part. Let's now delve into the architecture blueprint for the Vision Stays online scalable application. This comprehensive diagram provides a high-level overview of the components and services integral to our case study solution. At the heart of our architecture are three microservices, namely customer service, hotel service, and booking service. They will collect and store customer details, manage information for Vision Stays hotels, and handle reservation booking respectively. To ensure seamless deployment and management, we propose containerizing each microservice and deploy them into a Kubernetes cluster managed by OCI's Container Engine for Kubernetes, also known as OKE. To extend functionality to third-party vendors, we'll create two Oracle functions, namely create booking function and get hotel details function, and secure them using API gateway implementation. This centralized gateway acts as a protective barrier, regulating access to our backend microservices and ensuring that all incoming requests are handled securely and efficiently. Internally, these functions will interact with the microservices that are deployed within the OKE. All data generated by these microservices will be stored in Oracle Autonomous JSON databases instances. In alignment with our earlier discussion, the front end of our website will be hosted on OCI Compute Virtual Machine Instance. As previously mentioned, this setup will be complemented by a load balancer implementation to efficiently distribute traffic and ensure scalability. Also, as previously emphasized, security is of paramount importance. Our strategy involves bolstering the web application's defenses through OCI Web Application Firewall, ensuring robust protection against potential threats. In our journey to streamline the build, test, and deployment processes, we turn to DevOps practices and the OCI DevOps project resource as our trusted allies. Every code commit initiates a series of action within our CI/CD pipelines. As changes are pushed to our OCI DevOps code registry, build triggers automatically kick off build runs, facilitating creation of new artifacts or container images. These freshly minted assets are then securely stored in our artifact and container registry, which are ready for deployment. During the execution of our deployment pipelines, these stored artifacts or container images are seamlessly pulled from the registry. This ensures that the deployment process is smooth and efficient, with the latest version of our application components readily available for deployment. With such automation in place, we are not just deploying code, we are implementing deployment strategies like blue-green and canary deployments, ensuring minimal disruption and maximum reliability. This strategic approach enables us to deliver updates swiftly and confidently, meeting the evolving needs of our users while maintaining the stability of our application. Additionally, the booking service can utilize OCI's notification and streaming service to send email notifications to the hotel administration team for new bookings and store messages for downstream analysis. To safeguard sensitive credentials such as database passwords, we can leverage OCI Vault service for secure storage. In the next step, we'll establish events, monitoring, alerting, and logging systems to meticulously track the performance and health of the Vision Stays application. These observability services play a critical role in providing real-time insights into the application's operation and overall health. With OCI Event Service, developers can easily trigger code execution through functions, write to streaming service, or send alerts using notification, enabling intelligent response automation to changes within the infrastructure. Monitoring tools continuously access various metrics such as CPU and memory utilization, network traffic, and response times, allowing us to promptly identify any anomalies or performance bottlenecks. Additionally, alerting mechanisms can be configured to notify the appropriate personnel in the event of unusual activity or critical system issues. Furthermore, logging systems capture and store detailed information
about applications, events, and user interactions. This comprehensive logging data enables us to conduct thorough analysis, troubleshoot issues efficiently, and gain valuable insights into user behavior and system performance. By implementing these observability services, we can proactively monitor the vision stage application, promptly address any issues that may arise, and ensure optimal performance and reliability for our users. In summary, our architecture blueprint for the Vision Stays website case study solution integrates a comprehensive suite of OCI cloud native solutions, including microservice architecture, containerization, and container orchestration. Leveraging serverless computing and DevOps services, we've streamlined development processes with efficient CI/CD pipelines. Furthermore, the inclusion of API Gateway ensures secure access to backend microservices, while OCI core services provide essential infrastructure support. Combined with observability tools for enhanced monitoring, our solution embodies the pinnacle of cloud-native practices, empowering Vision Stays web application to scale and innovate with confidence in today's dynamic landscape. I hope you found this case study interesting. See you in the next lesson. Thank you so much for watching.
Hello and welcome to this lesson on microservices architecture overview. Let's start by understanding what are microservices. The term microservices is generally meant to describe an approach to software development that involves decomposing application functionality into individual components that can be deployed separately from each other and typically communicate via application programming interfaces or APIs. Microservices basically utilize integration, API management, and cloud deployment technologies, which gives developers the freedom to independently develop and deploy services as per their requirement. Microservices are used to design an application that is multilingual. This helps teams which work somewhat independently of each other. This allows developers to use different programming languages and technologies without affecting the overall architectural structure of the software development. One developer might use Node.js to code specific app feature and the other might use Python. That's absolutely fine. Loosely coupled with other services. In a loosely coupled environment, you can easily work with the least elastic component to address any slowdowns or performance gaps. Loose couplings enables the isolation of microservices that lead to better productivity. Easy to maintain and independently deployable. Following code is easier since the services are isolated and less dependent, which also makes it easier to deploy them in literal pieces without affecting other services. So when a change is required in certain part of the application, only the related services can be modified and redeployed. There is no need to modify and redeploy the entire application. Easily scalable and highly available. Microservices are easy to scale and integrate without third-party services. Although not a simple task, but maintaining high availability with microservices can be done using replication methods like load balancing techniques and using API gateways. Failure resistant. You can build resilient microservices by including fault tolerance policies in your code. For example, in a movie ticket application, different microservices might support scheduling, purchasing, and customer preferences. If one service fails, fault tolerance policies help limit the error and keep it from taking down the whole application. Let's take a look at a microservices architecture for a sample e-commerce application. The API layer is the entry point for all the client requests to a microservice. The API layer also enables microservices to communicate with each other using the HTTP, gRPC, and other TCP/UDP protocols. The logic layer focuses on a single business task, minimizing the dependencies on the other microservice. This layer can be written in different language for each microservice. As you can see, this e-commerce application makes use of 3 microservices. One is coded in Java, the other one in Python, and the third one in Go, which makes it multilingual. The data store layer provides a persistence mechanism, such as a database storage engine, log files, and so on. Developers can consider using separate persistent data store for each microservice. As you can see over here, there is a separate data store for container 2 and there is a separate data store for container 3 that is using Go. Typically, each microservice runs in a container that provides a lightweight runtime environment, and these can be scaled up or down as per the user requirements and managed using the orchestration tools like Kubernetes. Let's understand the difference between a microservices architecture and a monolithic architecture. In a monolithic architecture, the entire application is built as a single unit which contains the business logic, user interface, and data access layer. These three services are defined within the application as a single instance. So basically, these three services will share the same resources and database, which makes them dependent on each other. Problem here is, if one service within a monolithic application stops working, then the entire application will stop. On the other side, in the microservice architecture, the business logic is organized as multiple loosely coupled services, where each service has their own resources which make them independent autonomous services. So even if a single service crashes, it will not affect the other services running within the application. Let's take a detailed look at how microservices differ from monolithic architectures. So when it comes to unit design, microservices architecture are loosely coupled services, whereas monolithic architectures are designed, developed, and deployed as a single instance. When it comes to functionality reuse, microservices define APIs that expose their functionality to any other client, whereas in case of monolithic architecture, the functionality reuse is very limited. When it comes to communication within the application, microservices makes use of REST API calls based on HTTP protocol, whereas monolithic architectures make use of internal procedures and function calls. Talking about technological flexibility, microservices architecture offer better flexibility as they show support for multiple programming languages and framework that best suits the problem. Whereas in monolithic architecture, you have to write the entire application using a single programming language. Talking about data management, within microservices architecture, every microservice can manage their own data store, hence making it decentralized. Whereas in monolithic architecture, you must maintain a centralized database. When it comes to deployment, microservices architecture can be deployed independently. Every microservice can be coded and deployed independently of each other. Whereas in monolithic architecture, you will have to write the entire code at once and then deploy it. And again, if you have to make some changes, then you have to redeploy the entire application. Which is also why maintainability is easier in microservices architecture as you are managing small piece of codes at a time. Whereas in monolithic architecture, it's very complex to maintain the entire piece of code. Talking about resiliency and fault tolerance, microservices architectures show high resilience, whereas monolithic architecture show low resilience. And at the end, talking about scalability, you can easily scale each microservice independently of the other services. Whereas in monolithic architecture, you must scale the entire application. Communication mechanism in microservices architecture. As we all know, microservices are distributed in nature. So to communicate with one another, they make use of inter-service communication on network level. Each microservice has its own instance and processes. Therefore, services must interact using an inter-service communication protocol like HTTP, gRPC, or message brokers like AMQP protocol. Before we design our microservices communication, we should understand about communication styles. In general, there are two criteria to classify these communication systems, based on the type of protocol, that is either synchronous or asynchronous, and based on the number of receivers, which can be single or multiple. Synchronous communication is using HTTP, HTTPS, or gRPC protocol for returning synchronized responses. The client usually sends a request and waits for a response from the service, which means client code blocks their thread until they receive response from the service. Talking about asynchronous communication, in this case, these sub-processes are not logged and protocols that are compatible with many operating systems and cloud environments are used. The most popular protocol for this asynchronous communication is AMQP protocol, that is Advanced Message Queuing Protocol. So when using AMQP protocols, the client sends the message using message broker systems. The popular ones are Kafka and RabbitMQ. Remember, inter-service communication can result in a lot of network traffic. For that reason, serialization speed and payload size becomes more important. So if we are communicating between services internally within our microservices cluster, we might also use binary format communication mechanism like gRPC. gRPC is one of the best ways to communicate for internal microservice communication. The second classification criteria of microservice communication protocol is the number of receivers, distinguishing between one or many receivers. In case of a single receiver, each request must be processed by a receiver or a service. One example of this type of communication is a command pattern. And a good example in case of many receiver is the event-driven microservice architecture, which is based on a messaging agent or event bus interface that broadcasts the data updates among different microservices using events. Normally, microservices-based applications use systems that combine different communication styles. The most common type is a single receiver communication via an asynchronous protocol, with HTTP and HTTPS being one of the most used. Alright, to wrap up our discussion on this lesson, we covered what microservices are, we covered the differences between microservices and monolithic architecture. We also saw the different communication mechanisms used by microservices architecture. I hope you found the lesson useful. See you in the next one. Thanks for watching. Hello, I am Mahendra Mehra and I welcome you to this lesson on design methodology of microservices. In our previous lesson, we discussed how microservices architecture is a better approach over monolith approach to application development. The question is, how do you pull it off? One method which is extremely beneficial is the 12-factor app methodology. It was created by developers at Heroku back in 2011. So let's get started. The 12-factor methodology is a set of 12 best practices to develop applications which are supposed to run as a service. 12-factor app principles got very popular as it aligns with the microservices principle. Let's look at each of them. The first one is code base. This principle states that an app should be tracked in a single code repository and must not share the repository with any other application. Usually in microservices, every services have their own code base, and having an independent code base helps you to ease the CI/CD process for your applications. The next one is dependencies. All the application packages should be managed through package managers like SBT, Maven, or Gradle. For example, Maven requires us to describe a project dependencies in an XML file, typically known as Project Object Model or POM. Again, in a non-containerized environment, you can go for configuration management tools like Chef, Ansible, etc. to install the system level dependencies. But for a containerized environment, you can always go for a Docker file. Configuration. Configuration says that you must externalize the configurations from the application. All the configuration data should be stored separately from the code in the environment as variables and not in the code repository, and should be read in by the code at runtime. Having a separate config file makes it easy to update the config values without touching the actual code base, thus eliminating the need for redeploying applications when the config values are changed. You can use configuration management tools like Ansible or Chef to automate this process. Backing services. The 12-factor app can automatically swap the application from one provider to another without making any further modifications to the code base. Let us say you would like to change the database server from your on-premises MySQL to OCI database cloud service. To do so, you should not make any code changes to your application. Only configuration change should be able to take care of it. Build, release, and run. Strictly separate the build and run stages is what this factor promotes. You can use the CI/CD tools to automate the builds and deployment process. Docker images make it easy to separate the build, release, and run stages more efficiently. Images should be created from every commit and treated as a deployment artifact. Processes. By adopting the stateless nature of REST, your services can be horizontally scaled as per the needs with zero impact. If your system still requires to maintain the state, you can use resources like Redis, Memcached, or Datastore to store the state instead of in memory. Never assume that any cached in memory or on disk will be available during the future request or job. Port binding. Application should be self-contained instead of deploying them into any of the external web servers. To make the port binding factor more useful for microservices, You must allow access to the persistent data owned by a service only by the way of service APIs. This prevents implicit service contracts between microservices. Concurrency. This principle advocates to opt in for horizontal scaling instead of vertical scaling. Where vertical scaling requires adding additional hardware to the system, horizontal scaling works by adding additional instances of the application. In microservices architecture, by adopting the containerization, applications can be scaled horizontally as per the demands. Disposability. The system should not get impacted when new instances are added or existing ones are taken down. This is known as system disposability. Systems do crash due to various reasons. The system should ensure that the impact would be minimal and the application should be stored in a valid state. Services deployed in Docker containers do this automatically, as it's an inherent feature of containers that they can be stopped and started instantly. Development and production parity. You must always keep the development, staging, and production as similar as possible to avoid the risk of bugs showing up in the later stages of your software development lifecycle. Containers work well for this as they enable you to run the exact same execution environment all the way from local development through the production. Logs. Logs become paramount in troubleshooting the production issues or understanding the user behavior. Log provides visibility into behavior of a running application. Logs should be streamed to a chosen location rather than dumping them into a log file. Observability and monitoring help you achieve this in a microservices-based architecture, which we will be also covering in our later modules. Admin processes. The idea here is to separate the administrative task from the rest of the app to prevent one-off tasks from causing issues with your running applications. For example, doing data cleanup, running analytics for a presentation, or turning on and off features for A/B testing. After understanding microservices and differences between microservices and monolithic architecture, let us also look at the top benefits of microservices. The primary benefit of microservice architecture is its loosely coupled components. These components can easily be developed, replaced, and scaled individually. Microservices are not organized around technical capabilities of a particular product, but rather business capabilities, as the end goal is user experience and customer satisfaction. As with microservices, the choice of programming language can be multilingual. Also, the development teams can work in parallel on different pieces of code. It improves the productivity and at the same time the speed of deployment. Increased fault tolerance and fault isolation. Microservices offer fallback mechanisms so that in case one microservice fails, the other microservices around it won't get hampered and they can still make progress. Greater scalability and flexibility. This is one of the important features that microservices offer. Its ability to scale horizontally. This means that any deployed service can be duplicated in order to avoid slow execution bottlenecks. Simplified security monitoring. The ability to isolate each service facilitates better security management and monitoring. It's always easier to isolate threats with the modular arrangement. Autonomous cross-functional teams. Specific microservices can be assigned to specific development teams, which allows them to focus solely on one service or feature. This means teams can work autonomously without worrying what's going on with the rest of the application. Let's take a look at some of the drawbacks of microservices design. Microservices designs are more complex. Communication between services can be complex at times. An application can include dozens or even hundreds of different services, and they all need to communicate securely. More expensive than monoliths. For microservices architecture to work for your organization, you need sufficient hosting infrastructure with security and maintenance support. You also need skilled development teams who will understand and manage all of these services for you. Any microservice initiative requires organizations to make changes to their internal culture. Before they can start the migration process, there should already be a mature, agile, and DevOps culture in place. Microservices design presents harder debugging problems. Debugging becomes more challenging with microservices. With an application consisting of multiple microservices and with each microservice having its own set of logs, tracing the source of the problem can be difficult at times. Global testing is difficult. While unit testing may be easier with microservices, integration testing is not. The components are distributed and developers can't test an entire system from their individual machines. To wrap up, clearly there are many advantages and disadvantages of microservices architecture to consider. But it's important to consider how well this approach fits your organizational culture and goals. Implementing microservices could bring great results that are highly beneficial, particularly to large companies or complex business domains. I hope you found this lesson useful. Thanks for watching. Hello and welcome to this lesson on containerization overview. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. Containerization is a form of virtualization, operates by running applications in isolated user spaces known as containers. Notably, all these containers share the same underlying operating system. The container engine, pivotal in containerization technologies and container orchestration platforms, serves as the container runtime environment. It effectively manages the creation, deployment, and execution of containers. Now let's explore the magic of containerization. Imagine a container as a fully packaged and portable computing environment. It's like a digital suitcase that holds everything an application needs to run. Binaries, libraries, configuration files, dependencies, you name it, and the best part, it's all encapsulated and isolated within container. In olden days, running an application meant matching it with your machine's operating system. For example, Windows software required a Windows machine. However, containerization has rewritten this narrative. Now it's ancient history. With containerization, you create a single software package, a container that gracefully runs on any device or operating systems. What's fascinating is that these containers seamlessly run while sharing the host operating system. Now here's the techie part. The container engine is like a shadow, abstracted from the host operating system with limited access to underlying resources. Think of it as a super lightweight virtual machine. The beauty of this, the containerized application becomes a globetrotter, seamlessly running on bare metal, within VMs, or on the cloud platforms, without needing tweaks for each environment. Let's understand how is it different from virtualization. On one side, we have traditional virtualization. Picture this. It's like having multiple houses on a single piece of land, and each house or virtual machine has its complete setup, wall, roofs, and utilities. This setup, while providing isolation, can be resource intensive, with each virtual machine carrying its entire operating system. Now let's shift gears to containerization. The modern day superhero. Imagine a high-rise building where each floor represents a container. These containers share the same building or host operating system, but have their private space or isolated user space. Here's the magic. They are super lightweight, don't carry extra baggage of a full operating system, and can swiftly move between different floors. With containerization technology, there's less overhead during startup and no need to set up a separate guest OS for each application since they all share the same OS kernel. Because of this high efficiency, containerization is commonly used for packing up the many individual microservices that make up modern applications. Containerization unfolds a spectrum of benefits, delivering unparalleled portability as containers run uniformly across diverse platforms. This agility, fostered by open source container engines, empowers developers with cross-platform flexibility. The speed of containerized applications known for their lightweight nature, reduces cost, boosts efficiency, and accelerates start times. Fault isolation ensures robustness, allowing independent operations without affecting others. Efficiency thrives as containers share the OS kernel and reusable layers, optimizing server utilization. The ease of management is achieved through orchestration platforms like Kubernetes, automating essential tasks. Security remains paramount as container isolation and defined permissions fortify the infrastructure against malicious threats. Containerization emerges not just as a technology but as a transformative force, redefining how we build, deploy, and manage applications in the digital landscape. In closing, we have navigated the landscape of containerization, unlocking efficiency, scalability, and seamless deployment. Embrace the power of containers for a future-ready, agile infrastructure. I hope you found this lesson interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on Docker components. My name is Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. Let's talk about various Docker components. The image on the screen represents various components of Docker architecture that work together to achieve containerization goals. Talking about Docker client, a developer or a DevOps professional communicates with Docker engine through the Docker client, which may be run on the same computer as Docker engine in case of development environments or through a remote shell. So whenever a developer fires a Docker commands, the client sends them to the Docker daemon, which carries them out. The communication between the Docker client and the Docker host is usually taken place through REST APIs. The Docker clients can communicate with more than one daemon at a time. Docker daemon is a persistent background process that manages Docker images, containers, networks, and storage volumes. The Docker daemon constantly listens to the Docker API requests from the Docker clients and processes them. Docker registries are services that provide locations from where you can store and download Docker images. In other words, a Docker registry contains repositories that host one or more Docker images. Public registries include Docker Hub and Docker Cloud, and private registries can also be used. Oracle Cloud Infrastructure offers you services like OCIR, which is also called a container registry, where you can host your own private or public registry. Let's understand how virtual machines are different from containers. As you see from the diagram, a hypervisor or a virtual machine monitor is a software, firmware, or hardware that creates and runs virtual machines. It is placed between the hardware and the virtual machines, and it is necessary to virtualize the server. Within each virtual machine runs a unique guest operating system. VMs with different operating systems can run on the same physical server. A Linux VM can sit alongside a Windows VM, and so on. Each VM has its own binaries, libraries, and application that it services, and the VM may be many gigabytes in size. This technique provides a variety of benefits like the ability to consolidate applications into a single system, cost savings through reduced footprints, and faster server provisioning. But this approach has its own drawbacks. Each VM includes a separate operating system image which adds overhead in memory and storage footprint. As it turns out, this issue adds complexity to all the stages of software development lifecycle, from development and test to production and disaster recovery as well. It also severely limits the portability of applications between different cloud providers and traditional data centers. And this is where containers come to the rescue. Containers sit on top of a physical server and its host operating system, typically Linux or Windows. Each container shares the host OS kernel and usually the binaries and libraries as well. But the shared components are read-only. Sharing OS resources such as libraries significantly reduces the need to reproduce the operating system code. A server can run multiple workloads with a single operating system installation. Containers are thus exceptionally lightweight. They are only megabytes in size and take just seconds to start. What this means in practice is you can put 2 or 3 times as many applications on a single server with containers than you can put on a virtual machine. Compared to containers, virtual machines take minutes to run and are order of magnitude larger than an equivalent container measured in gigabytes versus megabytes. You should use a virtual machine when you want to run applications that specifically require a new OS. Also, when isolation and security are your priority over everything else. In most scenarios, a container will provide a lighter, faster, and more cost effective solution than the virtual machines. Let's discuss a few Docker commands that you will be using while you work with Docker. So in order to create and run a container, the command is docker run, and you can specify the image name that you want to run within the container. There are other parameters that you can pass like -p for ports, -d to run it in detached mode, and likewise. Starting a stopped container, you can use the docker start command followed by a container name or a container ID to start that stopped container. To stop a running container, you can use the docker stop command and provide container name or ID as an argument. To restart a running container, you should use docker restart command followed by container name or its ID as an argument. To get the details of a running container, you can use the docker inspect command and pass the container name and ID as argument. You can also see the container logs using docker logs command. To list all the running containers within your environment, you can use the docker ps command. And if you want to see all the running as well as stopped containers, you can do a docker ps -a. To remove a container, you can use docker rm command and you can pass the container name or ID as an argument. To wrap up our discussion, in this lesson we discussed Docker architecture, core components, and understood the difference between VM and containerization. We also looked at a few commands which are essential in order to interact with Docker daemon. I hope you liked the video. Thanks for watching. Hello, my name is Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. As part of this demo, we will be covering the Docker basic commands which you should be familiar with in order to create and manage Docker images for your applications. So let's get started. Alright, so in order to work with Docker commands, you need to have Docker installed on your local terminals. For all the OCI users, we have Cloud Shell which has Docker pre-configured in it. So I'll be making use of Cloud Shell to run you through these demos. In order to bring up your Cloud Shell, click on the icon on the top right corner. This will spin up a Cloud Shell machine for you and connect you with the Cloud Shell machine. Alright, so my Cloud Shell machine is up and I'll start using it for the demo. Just to make sure which version of Docker is installed on my Cloud Shell, I'll use the command docker-v. It says the version 19.03.11-OL is installed on the Cloud Shell. The first command that I want to show you is the docker run command. What this command does is it checks whether hello world image is available within my machine. If it is not, it will fetch this hello world image from the public Docker repository and then try to containerize it and show us the output on the screen. Let me quickly go ahead and hit enter. As you can see, the output says it was unable to find image, so it tried to pull this image from the Docker repository online. Once it completed pulling the image, you can see that the output is hello from Docker. Now to show you whether the image was downloaded on my machine or not, I can simply run a docker images command. As you can see, the Docker image hello-world was downloaded on my machine with the tag latest. It also gives this image an ID, which is a random string. And again, as you can see, this image was created 5 months ago. And in the last column, you can see the total size of this image. We can use the docker ps command to check any running container within the system. At present, there are no running containers, so the output is blank. You can also use the -a argument with docker ps to check all the stopped containers. So if you see, there is one container that exited a minute ago, and this is currently in the exited state. I can remove this container from my system using docker rm command, docker rm, and you need to pass the argument like the container name or the container ID to remove this container. So as you can see, the container ID I have copied from the first column and I'm using it as an argument to remove this container from the system. The moment I hit enter, this container will be removed and you will see that it returns the container ID once the command exited successfully. Now if we check using docker ps space -a command, the output is empty. Well, you must be wondering that the container ran and it exited after just printing hello world. Let's try to run a container and try to gain the shell access of it, for which we will be using a different image. So the docker run -it busybox sh, this command will basically pull the busybox image from the docker repository. It will containerize it, and since I have supplied the -it flag, this will basically connect me to the container in an interactive mode and give me the shell access of the container. Let me quickly hit enter and see the result. As you see, it was unable to find the image locally, so it tried to pull the image from the docker repository online. After pulling, it containerized the image, and now I have the shell access of this container. Here I can run all the different commands within this container. Let me quickly do a pwd to check the present working directory. I can also do an ls to check all the contents of the file system within this container. In order to come out of this container, you can use the exit command. The exit command will bring you out of this container. Now let me show you whether the container is running or not. Using the docker ps command, you can see the moment I exited from the container, it stopped the container and the container is no longer running. So in order to see if the container was exited, let me show you using the docker ps -a command, and you can see the container status says that it was exited 23 seconds ago. Also, one thing to note here is whenever you containerize an image, it gets a container ID as well as a container name. This container name is given by the Docker engine itself. Let us explore a few more Docker commands. For example, we have this docker run -d -p command in order to run a container and map its port to the outside world. The -p flag over here needs an argument where you have to specify the host port that you wish to map to that of the container's port. So we have mapped the host port 80 to the container port 80 in this command. Let me go ahead and hit enter. As you can see, the image is being pulled from the Docker repository and it's being containerized. And towards the end, it gives us the container ID that it has created. Alright, so now let me do a docker ps and see if the container is running. Yes, the container is running. As you can see, the container ID matches in the first column. And the container was created 14 seconds ago and the status says that it's up since 13 seconds. You can also see a new column which gives you details about the port mapping. It says that the port 80 of the host machine has been mapped to port 80 of your container. Let me quickly use a curl command to see if I can make connection with this port 80 on the container. What this curl command does is it tries to make a connection to port 80 on my host machine. And since I have binded port 80 on my host machine to that of containers port 80, let us see if we get some results on the screen. As you can see, the code of the web page is displayed on the screen. It is the limitation of Cloud Shell that it does not has a public IP assigned to it, which is why I chose to use curl command to show it to you in this manner. Let me quickly clean my screen. Now that I have a container running, I can stop this container by using docker stop command and passing the container ID as the argument. So the moment I hit enter, this particular container has been stopped. Now if I try to run the curl command again, it says connection refused because the container has been stopped. I can start the container by using the docker start command and giving the container ID as the argument. Now the container has restarted. So if I run the curl command again, I can see that it has made connection with my container port 80. Let me clean the screen. You can also use docker restart command to restart your container. This command will restart the container for us. Once the container restarts, it returns the container ID on the screen. The docker port command helps you see all the port mapping of a given container. So if I hit enter over here, you can see it says port 80 of my container is mapped to port 80 of my host machine. You can also see the logs of the container using docker logs command. So docker logs and the container ID will print on the screen the logs of the container. These logs can be used for troubleshooting purpose. To get detailed information about an object within the Docker container, you can use the docker inspect command. The output will give you detail of all the objects managed by this container. So right from the state information of the container to the image that is being used, it also gives you information about the CPU, the memory, and the other hardware information. It gives you information about different storages that has been attached to it. It gives you information like which command is running within the container. All the network settings information can be seen here. So basically, if you want to inspect your container to get details of all the objects that it manages, you can use the docker inspect command. To see the list of top processes running in your container, you can use the docker top command and pass the container ID as the argument. At present, there is an Nginx server that is running inside the container that can be seen over here. You can also run a command within a running container using the docker execute command. So the syntax is docker execute -it, and I've given the container ID followed by the command that I wish to run. So I'm trying to access the shell of this running container. Let's hit enter, and as you can see, I've got the shell access of this container. Remember, if you write exit within the container's shell and take you back to your original shell. But just in case, if you don't want to kill the container and exits its shell, you have to press Ctrl D. So what Ctrl D does is it brings you out of the shell, but at the same time keeps the container running. So if I do a docker ps, my container is still running. With this, we come to the end of this demo. I hope you liked the demo. See you in the next demo. Thanks for watching. Hello and welcome to this lesson on working with Docker images. My name is Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. Let's understand what a Docker file is. A Docker file is a text file that defines a Docker image. You'll use a Docker file to create your own custom Docker image. In other words, to define your custom environment to be used in a Docker container. You'll want to create your own Docker file when existing images won't meet your project needs due to different runtime requirements, which means that learning about Docker file is an essential part of working with Docker. Docker file is a step-by-step definition of building up a Docker image. It provides a set of standard instructions to be used in Docker file that Docker will execute when you issue the docker build command. Let's understand each of the commands used here. Every Docker file must start with a from instruction. The idea behind this is that you need a starting point to build your image. It can be from scratch or from an existing image available in the Docker registry. The run command is used to execute a command and will wait till the command finishes its execution. Since most of the images are Linux based, a good practice is to set up a directory you'll work in. That's the purpose of work directory line. It defines a directory and moves you in. The copy instruction helps you to copy your source code into the image. env provides default values for variables that can be accessed within the containers. If your app needs to be reached from outside the container, you must open its listening port using the expose command. Once your application is ready to run, the last thing to do is to specify how to execute it. You must add the cmd line with the same command with all the arguments you use locally to launch your application. This command can also be used to execute commands at runtime for the containers, but we can be more flexible using the entry point command. Labels are used in Dockerfile to help organize your Docker images. Labels are key value pairs and simply adds custom metadata to your Docker images. As you can see from the example, we have specified the key value pair as maintainer, which specifies who is the one maintaining this Docker file. Let's take a look at various Docker commands that will be handy when we work with Docker container images. In order to pull an image from the Docker Hub, you can use the Docker image pull command by specifying the image name as the argument. To build an image using Docker file, you need to use the Docker build command, and then you need to specify the Docker file path where the Docker file is stored. To build an image from a running container, you can use the Docker commit command and providing the arguments like the container name or the ID and then the image name that you wish to store it as. Tagging a Docker image. You can use the Docker tag command to tag your source image into the target image format. Pushing an image to Docker Hub. In order to push your image from local repository to your Docker Hub repository, you need to first log in into your Docker Hub, and then you can use the Docker image push command followed by the image name that you wish to push to the Docker registry. List container images. At any point in time, to check the number of images that you have in your local repository, you can use the Docker image ls or the Docker images command. Deleting an image from your system. In order to remove an image from your system, you can use Docker image remove or Docker RMI command by supplying the image name as argument to these commands. To wrap up, in this lesson we explored what is a Docker file. We also covered the syntax of a Docker file. We did a go through on the important commands to build a Docker image using a Docker file and how to push it into the Docker registry. I hope you liked the lesson. See you in the next one. Thanks for watching. Hello and welcome to this demo on working with Docker images and Docker repository. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. As part of this demo, we will be looking at what Docker file is, how to create an image out of a Docker file. We will also look how to deal with Docker repositories. We will be covering steps like how to pull an image from a Docker repository and how to push an image into your Docker repository. So let's get started. Alright, so I am logged into my Cloud Shell. As part of this demo, we will be creating a Docker image for our Python application. We will later containerize it and see it taking effect. We will also push this image to my Docker repository maintained on the Docker Hub online. So let's get started. Alright, so I have this application coded in Python. Let me quickly show you the application. This is my application, which basically prints hello world on the screen along with the hostname of the machine. I have also written a Docker file which will create a Docker image for my application. Let me show you the Docker file. So this is my simple Docker file. As you can see from the output, the from instruction tells it to use a Python base image. The work directory will create an app directory inside my image. The add command will copy everything that is present in the current directory location from where I will be running the docker build command inside the app directory on my image. Then I am using the run command to install all the dependencies that are required. I am also using the environment command to create an environment variable called name and passing it the value world. I am using the cmd command which tells the container that what is to be executed when the image is containerized. So let's quickly build the Docker image out of this Docker file. So the command on the screen lets you build a Docker image using the Docker file. Let me explain you the command. Docker build -t here stands for tag, that is basically the image name that you wish to give, and dot over here represents that the Docker file is present in the current directory. If your Docker file is present elsewhere, you have to provide the relative path to that Docker file. Let me quickly hit enter and let us see the progress of Docker build command. So from the output you can see that it is trying to first pull the Python image which was mentioned in the from instruction. After a successful pull of the Python image, it is executing the step 2, which was to create the work directory, that is /app, after which it copied all the content in my current directory into the app directory. Then it is running the pip install command to install all the dependencies. You can ignore the warnings. And then using the environment instruction, it created an environment variable called name with the value world in it. And finally, we have the cmd instruction taking effect, which will execute the app.py file, which is our application code. To see if the image was created successfully, we can do a docker images command. As you can see from the output, the image name Mahendra-demo is created. The tag is latest, the image ID is created for the image, and it was created a minute ago. You can also notice that a Python image is downloaded with the tag 2.7-slim. This image was initially downloaded as part of the build process, as you can see from here. So with this we saw how you can use Docker file to create a Docker image for your application. Now let's containerize this application and connect to it. Let me quickly clear the screen. In order to containerize your Docker image, we use the docker run command. Alright, so I'll be using the docker run command to containerize our image. Let me quickly explain you the syntax. Docker run command is basically used to containerize your image. In our case, it is Mahendra-demo. And I am using the -- name flag here to give my container a customized name. The -p flag over here is to map the container port to my host port. My application web server is listening on port 4000, so I am mapping the application ports 4000 to port 8080 of my host machine. Let's quickly run this command. Alright, now my container is running. In order to connect to my container 4000 port, I will have to connect to port 8080 of my host machine. So let me take you to the other instance of this Cloud Shell. And we will first see if the container is running using the docker ps command. Alright, as you can see, the container is running with image Mahindra-demo, and the port mapped is 8080 of my host machine to that of 4000 within my container. Now to check the output of my application, I will use the curl command. This curl command will connect to port 8080 on my host machine, which is mapped to 4000 on the container. So once I hit enter, my application prints hello world on the screen along with the hostname of the container. As you can see, the container hostname starts with 28, which is what we can cross check over here. Alright, with this we saw how to containerize your application using Dockerfile and Docker build command. Later we also saw how to containerize your image using the Docker run command. Now let me quickly show you how to manage operations like pull and push. This is my Docker Hub repository. As you can see, there are multiple repositories that I have created over here. I can pull an image from these repositories, or I can push an image into these repositories using the Docker CLI. Let's quickly pull an image from one of these repositories into the Docker CLI. Let's say I want to pull this image. In order to pull this image, I'll go to my CLI and use a docker pull command followed by the entire image name. So with the docker pull command, I'm trying to pull the my_website_nginx image from my Docker Hub repository, which is present over here. Alright, the moment I hit enter, it is trying to pull that image from the Docker Hub repository online onto my local terminal. Now, if I do a docker images, you can see the image is listed in my Docker local repository. Now, let me show you how you can push a Docker image onto your repositories which you manage online. Let us quickly create a repository. I'll click on the create repository button over here. I'll give it a name and give it a description. Also, you can choose from the visibility option, that is if you want the repository to be public or you want the repository to be private. Let me go ahead with the default one, that is public, and click create. Now you see that my repository has been created. In order to push an image into this repository, you'll have to use the command docker push and you'll have to provide the repository name. At present in my Docker client, I have an image called Mahindra-demo which I want to push into this repository that I just created. For that, I'll have to first tag my local image. Alright, as you can see, I'm using the docker tag command to tag my local image name Mahindra-demo to that of the name that I have maintained on the online repository, which is mahidocker 2018/OCI-demo, and I'm using v1 as the version of this image. Alright, so the tagging has completed successfully. Let us quickly check the same using the docker images command. There you go, we have a new image in our local repository with the tag mahidocker 2018/OCI-demo and the version indicates v1. Let me quickly clear the screen. Now, in order to push this new tagged image onto my Docker Hub repository, I'll have to first log in into my Docker repository. To do that, we need to use the docker login command. The docker login command asks you for the username and the password for your Docker Hub repository online. Alright, so I have logged in successfully. Now let me push the Docker image onto the Docker repository that we created online. So to do that, you use the docker push command. Let me go ahead and hit enter. And as you can see, the docker push command is in effect and it has pushed the Docker image onto the Docker Hub repository. Now let me quickly take you to my Docker Hub repository and let us see if we have an image listed under that repository with the tag v1. Let me quickly refresh this page. Great, so you can see a new image has been inserted into my Docker Hub repository, OCI demo, and it says it was pushed a few seconds ago. In order to delete an image from your local repository, you can use the docker rmi command. You cannot delete an image if there is already a container running that is referencing to that image. You must first stop that container, remove that container from the system, and only then it will allow you to delete the image. Let me quickly show it to you in practice. So I am running the docker images command to see the list of images that I have on my system. So let's say I want to delete this hello world image from my local registry. I can do that using the docker rmi command. So I'll run the docker rmi command and I'll have to specify the image name or the image ID to do so. Let me just use the image ID. Alright, now if I hit enter, it will delete the hello world image from my system. So the output says the hello world image has been deleted. Now if I run the docker images command again, you'll see that the Hello World image no longer exists in my local repository. With this, we come to the end of this demo. I hope you liked the demo. See you in the next one. Thanks for watching. Hello and welcome to this introductory lesson on OCIR, also known as Oracle Cloud Infrastructure Registry. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this session, we'll delve into the key features, benefits, and functionalities that make OCIR an essential tool for containerized application development and deployment. Let's get started. What is OCIR? OCIR is an Oracle managed registry designed to simplify the development to production workflow for developers. It offers a range of functionalities, serving as a private Docker registry for internal use, where developers can easily store, share, and manage container images. The strength of OCIR lies in its high available and scalable architecture. Leveraging OCI to ensure reliable deployment of applications, developers can use OCIR not only as a private registry but also as a public registry, facilitating the pooling of images from public repositories for users with internet access. What sets OCIR apart is its compliance with the Open Container Initiative standards, allowing the storage of container images conforming to the OCI specifications. It goes a step further by supporting manifest lists, sometimes known as multi-architecture images, accommodating diverse architectures like ARM and AMD 64. Additionally, OCIR extends its support to Helm charts. Security is a priority with OCIR, offering private access through a service gateway. This means that OCI resources within a VCN in the same region can securely access OCIR without exposing them to the public internet. Let's explore the key advantages offered by OCIR. Firstly, OCIR seamlessly integrates with the container engine for Kubernetes, ensuring a cohesive container management experience. In terms of security, OCIR provides flexibility by allowing registries to be either private or public, giving administrators control over accessibility. Furthermore, it is intricately integrated with IAM, offering straightforward authentication through OCI identity. Another notable benefit is regional availability. You can efficiently pull container images from the same region as your deployments. For high performance, availability, and low latency image operations, OCIR leverages the robust infrastructure of OCI, enhancing the overall reliability of image push and pull operations. OCIR ensures anywhere access, allowing you to utilize container CLI for image operations from various locations, be it on the cloud, on-premises, or even from personal laptops. Additionally, OCIR implements repository quotas. In each enabled region for your tenancy, you can establish up to 500 repositories with a cumulative storage limit of 500 GB. Each repository is capable of holding up to 100,000 images. Importantly, charges apply only for stored images. Before we move further, let's take a look at container registry concepts. What are images? Image is basically a read-only template with instructions for creating a container. It holds the application that you want to run as a container along with any dependencies that are required. Container registry is an Open Container Initiative compliant registry. As a result, you can store any artifacts that conform to Open Container Initiative specifications, such as Docker images, manifest lists, sometimes also known as multi-architecture images, and Helm charts. Let's understand what is a repository. It's a meaningfully named collection of related images which are grouped together for convenience in a container registry. There are different versions of the same source image which are grouped together into the same repository. For example, as you can see, we have a repository called Mahindra_project/Acme web app. Now you can have multiple images stored under this repository. The only thing that you need to keep changing is the image version. Every image version is given a tag, and the tag uniquely identifies the image. As in this case, we have two images for the Acme web app, which is 4.6.1 and 4.6.2. Depending upon your need, a repository can be made private or public. One important thing to note is that the user need to have an OCI username and authentication token before being able to pull an image from the OCIR. When working with repositories and container registry, you will find it helpful to have a clear understanding of following terms and how they relate to each other. Starting with the region key. The region key identifies the container registry region that you are using. For example, as you can see here, the IAD specifies the US East Ashburn region, whereas the US Phoenix one specifies the US West Phoenix region. A tenancy namespace is an auto-generated random and immutable string of alphanumeric characters. For example, the namespace of Acme Dev tenancy might be a random string, something like this on the screen. To find out the tenancy namespace of the current tenancy, on your OCI console, click on the profile menu and click on the tenancy option. The tenancy namespace can be retrieved from the value of your object storage namespace field. Repository name. The repository name is the name of repository in container registry to and from which you can push and pull images. Repository names can include one or more / characters and are unique across all the compartments in the entire tenancy. You should note that although a repository name can include / characters, the / does not represent a hierarchical directory structure. It is simply one character in the string of characters. As a convenience, you might choose to start the name of different repositories with the same string. As you can see in the example, we have started all the repos with the name project01. Perhaps ending in a / such as project01/. Such string is sometimes called as repository name prefix. But a repository named project01/Acme web app may not have a relationship with the project name project01/Acme web app/component2. Registry identifier. A registry identifier is the combination of your container registry region key and the tenancy namespace. It has the following structure: region key.ocir.io/tenancy namespace. As you can see in the example, we have a region key for the US Ashburn region, iad.ocir.io/a random alphanumeric string for our tenancy namespace. Moving on, a tag or an image tag is a string used to refer to a particular image in a known registry. The term image name is sometimes used as a shorthand way to refer to a particular image in a particular repository. In this context, an image has the structure repository name along with tag separated by colon. As you can see from the example, we have an image name with the repository name as project01/Acme web app, colon separated by the tag 4.6.3. A tag can be a numerical value or it can be a string, as in this case. Third example here, we can see that the repo name is my hello app and colon separated by the image tag, which is latest. An image path is a fully qualified path to a particular image in a registry. It extends the repository path by adding tags associated with the image. It has the following structure: region key.ocir.io/tenancy namespace/repo name :tag. And you can always refer Oracle official documentation to identify region key for the region you're working in. From the examples, we can see that there are two image paths belonging to the US Ashburn region, whereas the third one belongs to the US West Phoenix region. In conclusion, Oracle Cloud Infrastructure Registry, with its seamless integration, robust security measures, regional accessibility, and efficient